Okay, so the last three lectures we looked at various circuits and analyzed them under DC conditions. This lecture we start AC analysis. So let's start with the simplest possible circuit, one transistor, one drain resistance and a gate voltage applied so that the transistor is turned on. And now we want to use this circuit as an amplifier. So we want to apply a small AC signal and we hope that that AC signal will get amplified by this circuit. So we kind of guess correctly that whatever signal we want to apply, we'll apply at the gate and we'll look for the output at the drain. Now let's assume that we have an AC signal which is Vin equal to 10 cos omega t millivolts that we want to amplify. So let's say this is our AC signal represented by a voltage source. So the first question we must ask is, where do we connect this AC signal in our amplifier circuit? So the first question is, well, shall we do this? We'll connect, we said, well, we want to connect the signal to the gate. So we connect the signal to the gate and we hope that the output will give us an amplified version of the input. Okay, you pause and think for a couple of minutes about whether this is what we would like to do. The answer, of course, is no. Never ever do we want to do this. All right, so let's take a little digression. Look at a few simple circuits. Let us say we are given this circuit. This is all there is. There is a voltage source and nothing is connected to it. And I'm asking the question, how much is this voltage VA at this node and how much current IA is flowing? Of course, this is way too simple. And so the answer, of course, is that the current is 0 and the voltage is 9 volts. Now let's look at a next circuit where we short the node VB to ground and we ask the same question. How much is the voltage VB and how much is the current IB? Think about it. I assume you know the answer. This is, of course, we are shorting a voltage source. So the current will be infinite and the voltage VB is not defined, because if we look from here to this side, we see a ground. We look this side, we'll get 9 volts. So this is one of those circuits that violates Kirchhoff's voltage law, right? You know this is a short circuit. All right. How about this circuit? We have a 9 volt connected in series with a 10 millivolt. What is the current and what is the voltage? The answer is the same as this upper one, because we are violating Kirchhoff's voltage law. This voltage is 10 millivolts or 9 volts. It's neither actually. It's undefined. An infinite current flows in this circuit. All right. Okay, let's look at current sources. These will be relevant later, not for today's lecture. But while we are at it, let us look at these. Okay. So this is called a dual of the voltage, open circuit voltage circuit. So what is the current here and the voltage here? The voltage is 0. The current is 9 amperes. All right. Nothing wrong with this circuit. It is a perfectly valid circuit. Current sources can be shorted to ground. All right. Of course, this is a most valid of circuits. Current is flowing through a 5 ohm resistor. So VB will be 45 volts and the current will be 9 amperes. All right. So let's compare these two. It is important to recognize this, that the voltage VB is 45 volts, the voltage VA is 0 volts across the same current source. So we conclude, as I assume you know, this is kind of trivial, that the voltage appearing across a current source can take any value depending on what is connected to it. Here it is a short circuit, so the voltage is 0. Here it's a 5 ohm resistor, so the voltage is 9 times 5. If we change this resistance, the voltage will change. Alright, one last circuit. If this is a circuit, a current source is not connected to any resistance. This is an open circuit here. What is the voltage and what is the current? This is the equivalent of the short circuited voltage source. So the answer is that, what is the answer? The voltage becomes infinite, alright, and the current is not defined, because if we look at this side we get 0 current. If we look at this side we get 9 ampere, so we're kind of pushing 9 ampere into an open circuit, which is impossible. We are violating Kirchhoff's current law at this node, alright, and so we arrive at the infinite voltage by saying that suppose we have a resistance R, and if we keep increasing R, VB keeps increasing, so as R tends to infinity, the voltage tends to infinity. So the voltage across an open circuited current source is infinite. The current is not defined. Alright, these are of course theoretical circuits. They have meaning only on paper, or in some ways they don't have any meaning at all. Alright, let's go back to our circuit. So if we connect this voltage source directly, directly to the 9 volts, we have a 10 millivolt connected directly across a 0.9 volt, and that is effectively a short circuit, and infinite currents will flow and this voltage will be undefined. So none of this we want. Therefore, the question remains, where do we connect the AC signal source in this circuit? Alright, and I assume you know the answer, or at least you've done the answer in your some earlier electronics course. So let us think about it. What do we actually want in this circuit? We want that this transistor stays on, for which some gate voltage is required, and then at the gate we want this AC voltage to be added to the 9.9 volts, so that additional point V in causes an additional AC at the output, and that additional AC is an amplified version of the V in. That is what we want. So another way of saying it is, we want the AC to ride on top of the DC, or in other words, we want these two voltages to add, the 0.9 volts and the V in to add. So how is this done in in discrete circuits? In discrete circuits, we put a coupling capacitor, as you have seen before. And this is done mostly in bipolar transistor amplifiers, although I am showing it here for a MOSFET. So the way we generate the 0.9 volt DC is we use a resistor divider, and this 0.9 and 2.1 will give us a 0.9 volt here DC. Then we'll put a capacitor which decouples the DC from the AC, or which couples the AC to the DC, depends on how you look at it. Basically the 0.9 volts stays even when we connect the AC, because the capacitor acts as an open circuit for the DC, but it allows the AC to pass through, so that at this node the voltage is 0.9 volts plus V in. As you've seen this before, I'm not spending any more time on it, and in any case our course, as you remember, is CMOS analog IC design. This is of course an integrated circuit design. It is not a discrete transistor amplifier design, and so we see the connection in the next slide. Alright, the value of CG has to be chosen so that for the AC signal applied is basically acts as a short circuit. Of course, there are no short circuits, so we say, well, its impedance must be extremely small compared to other impedances in the circuit. So let us say that we want the impedance of the capacitor to be 1 ohm, And of course, this is a function of the impedance of a capacitor is a function of frequency. So we have to know at what frequency we are going to use this amplifier, which means we need to know the frequency band of the input signal. So let us say we are amplifying an audio signal which goes from 20 hertz to about 20 kilohertz. And so we say the impedance of CG for 20 hertz to 20 kilohertz must be less than or equal to 1 ohm. And of course, the largest impedance will occur at the smallest frequency. So we say at the smallest frequency we find the impedance. So that is this. So we say 1 over omega C must be equal to 1 ohm. So C must be equal to 1 over 1 ohm into 2 pi into omega. So 1 ohm 2 pi 20 hertz, which gives us 8 millifarads or 8000 microfarads. So when we are going to use this circuit as an amplifier for audio signals, then we will put a capacitance of about 8000 microfarads here to make sure that the capacitive impedance does not degrade the signal amplitude. Alright, let us think about doing this in an integrated circuit. So 8 millifarads is what we want. So let us think of fabricating an 8 millifarad capacitor in a 180 nanometer CMOS technology, which has TOX equal to 4 nanometer, which I think I have mentioned in one of the earlier lectures. So can you calculate the area required of this capacitor on a chip to obtain a value of, so we need a value of 8 millifarads. The oxide thickness is known. Can you find the area? Okay, take a couple of minutes. So we will basically see is epsilon A by TOX and find the A. Okay, I'm continuing. So we do that. So we get 8 millifarad equal to epsilon naught epsilon ox by TOX into A. So A is equal to 8 into TOX by epsilon naught epsilon ox. So 8 milli into TOX is 4 times 10 raised to minus 7 centimeters. So I'm doing everything in centimeters. Epsilon naught is 8.85 10 raised to minus 14. Epsilon ox is 3.9. So if you calculate, you'll get 9270 centimeters squared. So if I take the square root, it will come out to be about 96 centimeters by 96 centimeters. So this is the area required to fabricate a capacitor of 8 millifarads in a 180 nanometer technology. 96 centimeters, that's almost 1 meter. So you need a 1 meter by 1 meter chip size to make an 8 millifarad capacitor. Of course, the typical chip size is 1 centimeter by 1 centimeter. Where is 1 centimeter? Where is 96 centimeter? The point, of course, therefore, is that coupling capacitors are just unfeasible to be fabricated on an integrated circuit, especially for low frequencies. All right, these are audio frequencies, 20 hertz and all. All right, that's one. If, for example, we wanted to do a coupling capacitor for RF circuits, and let's say the frequency we're looking at is 2 gigahertz. So instead of, so let me go back. So instead of the 20 hertz here, if we had 2 gigahertz, which is what 10 raised to 8 times. So this will go down 10 raised to 8 times. Then we need 8 picofarads instead of 8 millifarads. I think that's correct. This looks like 9. Okay, yeah, whatever. I think this is correct. So we need 8 picofarads, and if you do 8 picofarads here, then you'll get an area of 30 micro by 30 micrometer, which is possible on a chip. So what this means is that for RF integrated circuits, one could fabricate coupling capacitors, and therefore one could use a scheme where the AC is coupled to the DC with a coupling capacitor. But for lower frequencies, and our focus will not be RF, because RF is a whole different way of designing circuits. So we'll do what one might call as baseband or whatever, megahertz, kilohertz, like that. Then fabricating coupling capacitors is not possible. All right, so therefore that's why different biasing schemes have to be used on integrated circuits. All right, with that, so what we are going to do for now, all right, for the next few lectures, is we are going to pretend, or we are going to cheat. We are going to say, well, let us just put both these voltage sources in series. Now this is practically not possible, because generally all voltage sources that we encounter in real life have one of the terminals grounded. Floating voltage sources, as this one is, floating means neither terminal is grounded, are not common. They are very rare, and we cannot assume floating voltage sources for designing general purpose circuits. But for now, just to avoid getting into the issue of the coupling business, we are going to pretend that the AC voltage source is floating and go ahead and do our analysis. The problem is very fundamental of coupling AC and DC, and there are two ways that this has been resolved for individual systems. One way to resolve this is to have a dual power supply. So you'll have a plus VDD and a minus VSS. So for example, here we have only a plus VDD and ground. So instead of ground, if we had a minus VSS or minus 3 volts, then we could design the circuit so that the DC voltage required at the gate is simply 0. Because if this is negative, then the gate voltage could be 0, in which case this 0.9 volt is not required, and we can only connect the AC directly to the input of the amplifier circuit. So that's one way this is resolved. The other way it is resolved is by introducing DC shifter circuits, and we'll really not look at this second one in this semester. Maybe at another time you will study this. In fact, we will not look at the dual supply also most of this semester. So we are basically not going to discuss the coupling of DC and AC in this circuit, but we just so you know, these are the ways that DC and AC coupling is handled in integrated circuits. Our purpose is to apply the AC on top of the DC and analyze the circuit. So let's get on with the analysis now. Before we get into the analysis, I want to introduce a convention of symbols. So I try to follow this symbol, but I don't promise that I'll always follow it. So the symbols are that now that we have DC as well as AC or small signal voltages, and then the total, which will be the sum of these two, this is the terminology we'll follow. So if the letter is capital and the subscript is capital, it's a DC quantity. If the letter is small and the subscript is capital, it's a total quantity, which is a sum of the DC and AC. And if both are small, it is a small signal or AC quantity, and that holds for currents and voltages, all currents and voltages in the circuit. All right, well, with this terminology, the question now we are asking finally is, given this circuit with a small signal voltage on top of a DC voltage, we want to find the total drain current, the AC plus the DC, and the total drain voltage in the circuit. So we want to analyze this circuit. All right, so we begin by saying, okay, the gate voltage is given, so that Vin is some 10 cos omega t, and we want to find the drain current and drain voltage. So we say, okay, let's start with the simplest equation. Of course, we'll assume saturation for now, and we'll come back later. For now, let's assume that the transistor is in saturation. So we write the saturation region equation, and we know VGS. VGS is the sum of the AC and the DC, and I'm calling this mu and Cox W by L as beta just for brevity. So we get beta by 2, and then VGS is equal to capital VGS plus small v in, where capital VGS is 0.9 volts. All right, so we get this equation. Now we expand the square out with VGS minus VT as one term and Vin as the other term. So we get beta by 2 VGS minus VT the whole squared plus 2 VGS minus VT into Vin, which is this term, plus Vin squared. Alright, so beta by 2, beta, that 2 goes away. And so we get this term, and the Vin term and the Vin squared term. Now we say if Vin by 2, which is this term here, is much less than VGS minus VT, or vice versa, if capital VGS minus VT is much greater than Vin by 2, then, so we are comparing the second and third term. So if we take the beta Vin out, then we'll get VGS minus VT plus small Vin by 2. Then we say if this Vin by 2 is much smaller than VGS minus VT, then we can ignore this last term. And then we get this term plus this term. Alright. And this is called the small signal approximation, that the AC signal that is applied is small in magnitude compared to this VGS minus VT, which is incidentally the overdrive voltage. I'm not sure if I've mentioned that term before. Anyway, yeah, I will mention it later in this lecture. Alright, so that is called the small signal approximation. And if we make the small signal approximation, then presumably you remember that the response of the circuit to AC signal becomes linear. Linear because the drain current becomes linearly proportional to the AC input signal, because we are ignoring the square term. Alright. Alright, so let us now formalize this. Alright, this whole small signal analysis. So we say, well, most generally speaking, the drain current of a MOSFET is a function of 3 voltages: gate source, drain source, and the body source voltages. Now if we have a DC plus an AC signal applied, then we can write each of these voltages as the sum of the DC and the AC voltages that exist at the each of the terminals. Then we expand ID as a Taylor series, and I assume you know Taylor series. So we say ID can be written as capital ID, which is the drain current at the DC voltages VGS, VDS, VBS, plus the partial derivative of ID with respect to VGS times the small VGS, which is this, plus the partial with respect to VDS times the small VDS, plus the partial with respect to VBS, first derivatives. Then all the second derivatives, the second derivative with respect to VGS, then partial VGS, VDS, VDS, VBS, VGS, VBS, and then the third derivatives, fourth derivatives, it go on till infinity. That will be the Taylor series. So this is a most general expression for the drain current when a DC plus another AC exists in the circuit. Then we make the small signal approximation, which is to say that all the second order and higher order terms are much smaller than the first order terms. All right, so these 3 are the first order terms, and all the higher order terms are much smaller than the first order terms. So in effect, we are saying that VGS is so small, for example, that VGS squared is much smaller than VGS, and so on and so forth. Okay. So with that approximation, we get ID approximately equal to only this first line. So we write that again here, it is only the first line. Now with this, we define, so this is of course approximate, we define 3 quantities so as to be able to write the same equation in this form, where GM 1 by Rho and GMB are defined to correlate these 2 equations. So we say GM is del ID del VGS, 1 by Rho, which is here, is equal to del ID del VDS, and GMB is del ID del VBS. So these become definitions of these 3 terms, which I am assuming you have seen before. GM is a transconductance, Rho is the output resistance, GMB is the body transconductance. Okay. This equation, of course, is an extremely important equation, and that's why I've put it in blue. It says the following: if we apply only DC voltages to a circuit, then the drain current will be ID, capital ID. So if there are no small AC signals applied, then these three are zero and we get only the DC term. On top of these DC, if we apply small signal AC signals, small signal AC voltages, then due to these AC voltages, we get the small signal AC terms. Alright, these are the small signal terms due to the AC signals applied. And the total drain current is the sum of the DC and the AC. What is this procedure called? Or what is this theorem called? It is called superposition. Alright, so we have actually applied superposition to a nonlinear circuit. How did this happen? It is because we used the small signal approximation and we ignored all the nonlinear terms due to the AC signal. Alright, so that the equations for the small signal applied became linear. For the DC circuit, the nonlinearities were not ignored. Alright, so let us remember this. ID is the complete ID equation that we have used, which is a nonlinear equation. We did not mess with that. So this equation only says that the ID is whatever it is due to the DC circuit, including all the nonlinearities. On top of it, when we apply a small signal, then the total current, and in fact, so therefore all currents and voltages in the circuit can be written as the sum of the DC plus the currents and voltages due to the AC signal. Alright. Alright, so superposition can be applied in this specific case where there is a DC on top of which a small AC is applied. Alright, so that is what we have proved here, which in some form or another you have done before. So for most of you, this is just a revision. One important note on a different subject is that the equations we have derived, we did not assume that the transistor was in saturation. We simply said, so let's go back. This is the equation for ID, we said. We did not say whether the transistor is in saturation, or we did not use the saturation or triode region equations. Therefore, this is valid whether the transistor is in saturation or triode. Alright, this is very important to remember. The equation is valid. Of course, the expressions for GM, RO and GMB will be different depending on whether the transistor is in saturation or triode. Alright. Alright, another point I want to make. So henceforth, we will use this small signal approximation to do all our AC analysis. So whenever we have an AC signal present, we'll assume the small signal approximation and use all the superposition methods to solve the circuit. Sometimes even when the AC signals are not small. Alright, what happens if they are not small? Then of course our approximation breaks down and the second order terms and maybe third order terms in the Taylor series expansion are no longer negligible and they must be included. So for example, if our input signal is VA cos omega t, then the output signal could perhaps be written in this form if the nonlinear terms are included. So there will be a linear term which is A1 cos omega t. But there will be nonlinear terms which will cause the square term, the cube term, etc., etc. And if we write the cos squared and cos cubed, convert them, then we could write this in this form. So A0 plus A1 cos omega t plus A2 cos 2 omega t. And we can correlate the capital A's to the small a's. What therefore this means is, as the AC signal magnitude becomes larger, the nonlinear terms will become relevant, and when the nonlinear terms become, well, significant, and when that happens, for an input signal at a frequency omega, the output signal will have components at 2 omega, 3 omega, 4 omega, etc., etc. And these are called as harmonics, right? So nonlinearities cause harmonics, and harmonics cause distortions in the output. So if I have an audio signal of whatever frequency, then at the output I'll get an audio signal that not only has omega but 2 omega, which will basically distort the original signal that was applied. Alright, so the effect of nonlinearities, or the effect of the input signal not being small anymore, is that it causes distortion in the output. Now the study and analysis of distortion is, it's a very highly complicated and a very high level study, and generally one doesn't do this in an, even in an MTech curriculum. If those who are interested would do it at a PhD level. So we are not going to do this. All right, we just be aware that if our signals are not small, they would have caused harmonics and distortions. We'll simply ignore them as far as this course is concerned. All right, so let's get back to our analysis. So we wrote this equation. Now let us derive expressions for GM-RO and GMB for our MOSFET in saturation. We'll derive them in saturation. I am leaving this as homework for you to derive them in the triode region. All right, so let's find all these three quantities. So we start with ID and then we differentiate the ID expression. So ID is this, and I've included this 1 plus lambda VDS term. We'll include, not include, we'll keep changing. In fact, for GM, so GM is del ID, del VGS. So that is differentiating ID with respect to VGS and keeping VDS constant. So we differentiate with VGS, the 2 comes out, the 2 cancel. So we'll get mu and C ox W by L, VGS minus VT. This stays. Generally speaking, this 1 plus lambda S is ignored while calculating GM. All right, so although I have written it here, henceforth we'll ignore it. So we'll write GM simply as mu and C ox W by L into VGS minus VT. All right, forget the 1 plus lambda, it's too complicated, so we won't worry about it. Now this expression can be written in 3 different forms by using the ID expression. All right, so if we substitute for VGS minus VT from here in terms of ID, then we can write GM also as 2ID over VGS minus VT, or we could also write it as square root mu and C ox W by L 2ID. So you please spend a few minutes to convince yourself that all these 3 expressions are equivalent with this expression for ID, ignoring the 1 plus lambda VDS. These are very important, and over a period of time it will be good if you just kind of memorize them. Generally what happens is you use them so often that they just become a part of your memory without having to memorize. But I'm emphasizing that you must know these expressions. All right, so let's find RO. So 1 by RO is del ID del VDS, and that is, so mu and C ox W by 2L, VGS minus VT stays. The 1 plus, let me go back. So 1 plus lambda VDS is what we differentiate with respect to VDS, and so all that is left is lambda. So we get this. Again, we cheat. So we say this is equal to lambda times ID. So we are saying this is ID, and we are ignoring the fact that ID is actually this multiplied by 1 plus lambda VDS. All right, so all these are just kind of engineering approximations to simplify our final expressions for these quantities. So RO is written, 1 by RO is lambda ID. So RO is 1 by lambda ID. So this is another expression to remember for ever and ever. And then GMB is del ID del VBS. So again, we ignore the lambda term. So we get, okay, so how is ID dependent on VBS? Where is VBS? There is actually no explicit VBS in the ID equation. But if you recall, the threshold voltage is a function of the body source voltage, and that we have talked about the body effect in relation to the threshold voltage a few lectures ago. So the dependence of ID on VBS comes from the threshold voltage. So when you differentiate, we are differentiating basically with VT as the variable. So we'll get this expression, and because there's a minus sign here, there's a minus here. So you'll get minus here W by VGS minus VT del VBS. And that is incidentally, this is GM mu n Cox W by L VGS minus VT. So we can write this as minus GM del VT del VBS. And we have derived VT in terms of VSB actually, but these ID is always written in terms of VBS, so there will be a negative sign somewhere. And yeah, you go through this, eventually you will get GMB equal to GM into gamma by 2 square root 2.5 plus VSB. All right, so this is what you'll get. So this is VSB, but this is VBS. This is just convention. So let us simply follow this convention. In any case, most of the time in this course, we will be ignoring GMB. We will be focusing on RO and GM. All right, so with these three now, we can draw the small signal equivalent circuit of the MOSFET. All right, so this is our MOSFET. And for small signal, we have three terms, GM VGS, RO and GMB VBS. All right, and RO is a resistance while the other two are current sources, because this circuit element or this current depends on a voltage elsewhere. This current is dependent on the gate source voltage. This current is dependent on the body source voltage. This is dependent on the drain source voltage. Therefore, this can be represented simply as a resistance. All right, so this and again, you've seen this circuit before, I'm sure. So we've just kind of derived this from scratch. All right, so this is the small signal equivalent circuit, which we will use now onwards to analyze circuits for the AC conditions. Now again, note that this is the so-called low frequency small signal circuit that we have derived. Later in the course, we will derive a high frequency circuit which will include capacitances. So for now, we are ignoring capacitances and we are doing a low frequency small signal analysis. All right, and as I said, for most circuits that we analyze, we'll assume that the body source, we'll not assume that the body source voltage is zero, but it will turn out that the body and source are shorted together. Therefore, VBS is zero, and if VBS is zero, of course, the GMB VBS source is zero, and this becomes an even more simplified small signal circuit. All right. So next lecture, we'll use this small signal circuit to analyze various amplifiers.